Now, with energy, the key thing that we look for is different types of energies we have. So the first one we have is potential energy. And the second one now is kinetic energy. So what is basically the difference between the two? So now this is energy possessed by an object due to its position. Very, very important. And now kinetic energy, energy possessed by an object due to its motion. So there are key things that we are looking for here. The first one is possessed by or due to the position of the object. The key other thing here is now due to its motion. So what does this basically say to me? This says to me the object in this instance should be moving. So for potential energy, it will move, but we need now to have a reference point. So a reference point will be a point where we check exactly the position of that specific object. So now, how can one calculate this? We use now the equation EP is equals to mgh. We use now EK is equals to half mv squared, where now mass, which is in m, must be in kg, and g now is gravitational acceleration, which is 9.8 meters per second, and then h is height, which now must also be in meters. So with this being said, it says now I can only use this equation provided that I have the SI units as they are. But what will be the SI unit now of energy? The SI unit of energy is joules, and we just say now this is a capital letter J. We further move on to say we also have the mass that must be now in kg. We also have now V, which is the speed, and this now must be in meters per second. So the only way of me using this equation is to ensure that I have my correct SI unit. For me to use EK is equals to half mv squared, my SI unit should be meters per second for the speed. So with that being said, it says these two equations are the important equations that one needs to take note of. These are the two important equations that we are going now to be in a position of applying them now correctly. Thereafter, we now want to say at number 1 and now at number 2, key thing, which is now the principle of conservation of mechanical energy. So this principle, mechanical energy. So this principle, we must be in a position of applying. We must be in a position of also stating it. So what does it say? It says now the total mechanical energy, the total mechanical energy in an isolated system is conserved or remains constant. So with this being said, remains constant. With this being said, it basically says to me, I need now to highlight the keywords: total mechanical energy in an isolated system remains constant or is conserved. If I now omit any word or any keyword in this statement, then I'm going to lose the 2 marks, because we usually mark this one as 2 or 0. So the key idea is have your key important words within the description itself. But now it says something here now about the total mechanical energy. Can one be able to say EP or EM is equals to EP plus now EK? What is this? This is just now mechanical energy. So mechanical energy is just the sum of kinetic energy and potential energy. So when we talk that now it is conserved, it basically says before and after the mechanical energy should be the same. So I can be now in a position of deriving an equation EP plus now EK at point A is equals to EP plus EK at now point B. Some books will prefer using at the top, at the bottom, but my point is we need to know now the reference point that we are looking at. So for any reference point thereof, this will allow us to fully understand how to apply conservation of mechanical energy. It will just be an issue of where are we in our question, or in terms of the statement now that is given. So I'm going to give you some time, about 50 seconds for you now to digest this. And if you have questions, you can feel free to ask any question you have. Kananelo, are you fine?
Yes, sir.
Thank you very much. Ratanang, are you fine?
Yes, sir.
Thank you very much. Then we can stop the timer and move. Now, when we move to the next section of this, it basically says, to what type of questions can one apply the conservation of mechanical energy? So allow me to go back to this specific slide here. So when we look at this summary, we can apply conservation of mechanical energy when we have now objects moving vertical. That is now at example number 1. I am here. Let me change the color. I am now on this one. So we can apply when we have objects moving vertically, but it will just be an issue of checking exactly where is your point A and where is your point B. We can apply now, check at example number 2, object moving on an inclined plane. We can also apply for a pendulum. We can also apply now for a roller coaster. So with a roller coaster, we also need now to identify point A and point B. If we are able to do that, everything now becomes nice and easy for us to fully understand. So remember, these are just examples, but in most cases, the examiners will try now to cover example number 1, 2, 3, and also 4. So you do have now the PDF notes of this. Kindly just go through them and just check how one can go about that. But there's a key thing that we need now to be understanding. For us to apply the principle of conservation of mechanical energy, we need now to look for the keywords. Very, very important. First thing, no friction. Ignore friction. No air resistance. So if there is no friction, no air resistance, then we can easily apply the conservation of mechanical energy. If I am not told that, then I will not be in a position of applying the conservation of mechanical energy. So one of the key hints will be, am I told to ignore the effects of friction? Am I told that there is no friction? If there is no friction, then automatically it says there are 100% chance that the system is isolated. And if the system is isolated, definitely mechanical energy is conserved. Now, one will ask, what is now isolated system? Isolated system is a system in which the net external force is 0. Very, very important. So you must also know the definition of an isolated system thereof. So this is basically a quick summary of one trying to explain in detail what are the key concepts that one needs to start looking for when working with energy and conservation of mechanical energy as well as mechanical energy. So with this being said, let's expose ourselves to an exam type of question. This is what we explained and we did as now example number 1. But we are going now to look at example or question number 5. So with this, it's 13 marks. So I'm going to give you 7 minutes, or let's make it 10 minutes for you to try it on your own, and then we'll come back and discuss. So I will give you 10 minutes for you to do it. It looks scary because it looks like a wave, and we did waves a couple of weeks ago. So, but now you must just check what the questions are and be in a position of surely trying to answer this one. So I'm going to give you 10 minutes, and don't forget to kindly send your answers to me on my personal number. Then I will be able to assist you the best way I can. So your time starts now. A steel ball. Let me change the pen to red. A steel ball of mass 5 kg is rolling on a frictionless surface. So what does this tell me basically? It tells me that the system is now isolated. In this instance, when I'm working with energy. So already it says I'm in a position of applying the conservation of mechanical energy. When when the ball reaches point A, its mechanical energy, EM at A, is equals to 250 joules. That is now the information that is given. And then at 5.1, they say now state the conservation of mechanical energy in words. So now, like I said, your laws and your definitions must be now 2 marks. These are the non-negotiables. So what can one say in this instance? It's easy. The total, okay, let me change the pen. The total mechanical energy of an isolated system is conserved. These are the keywords that now we are looking for. Total mechanical energy, isolated system, is conserved or remain the same. And then that will get your 2 marks for that. Now, what about 5.2? Use your knowledge of the principle of conservation of mechanical energy to write down the kinetic energy of a steel ball at point, I believe. Okay, and let me do this. Now, as I was saying, at 5.2, they say now use your knowledge of the principle of conservation of mechanical energy to write down the kinetic energy of the steel ball at point B. Now remember what we said. We said now, when I look at an isolated system, if this here is my mechanical energy up to there to B. So EM is equals to, okay, let me just try to do it for you. 5.2.1. We are going to do it with a calculation so that we exactly see how we got to the answer. So we have EM, which is equals to EP plus EK, but we are told that the mechanical energy is 250. And now at point B, because it is now at the bottom of the ground, it means my EP will be 0. And now what is left is my EK, and now my EK will just now be 250 joules. So this is now an easier way of looking into it, because now they give you 2 marks for that. So instead of just saying it is going to be 250, it's just an issue of checking, like we did say, what is happening at point A and what is now happening at point B. So because of that, we are in a position of saying we will get that answer of 250, because we know at the bottom or at the ground, now the height becomes now what? 0. So this will just be mgh, and everything multiplied by 0 will be 0. Then my EK will be equals to 250 joules. Now, furthermore, at 5.22, now check what they are asking us. Calculate the speed of the ball at the instant it reaches now point C. So this is more of like a roller coaster type of a question. We are told here, we are looking at these 2 points, A and C. So what are we told? We have 2 points with A included. So it becomes now example 4 which is more of a roller coaster type of a question. So I am going to say now the mechanical energy at A should be now equals to mechanical energy at C. Why is that the case? Because remember, mechanical energy is now conserved. How do I know? I'm told that I am working with a frictionless surface. So now I am in a position of saying, if this is the case, I know now that mechanical energy at A is equals to 250. I can easily substitute the 250. But mechanical energy now at C is basically mgh plus now what? Half mv squared. What is our mass? Our mass is 5 kg. 5 kg. G is 9.8, is a constant, and then we are told our height, it's now what? 5 meters, and now plus half of 5, and they want us to calculate the speed, which is now v squared. So what does this say? This says basically I can do the mathematics and solve everything, and I will find my v, which is equals to 1,41 meters per second. So this will now be my answer for 5.22. And with that being said, it says to me, I would be now in a position of getting 1 mark for the 250 and 1 mark for the substitution, 1 mark also there and another 1 there, and the final mark should be 4 for the formula, and now this becomes 5/5. So it was an easy question, but we just needed to understand where we are in terms of the equations or in terms of our reference point. So for the last one, which is 5.3, what do we know? We need now to calculate the mechanical energy at D. So let's calculate the mechanical energy at D. We are at D. EM is just now EP plus EK. So this basically says EM at the top will be now EP, it's mgh will be 5 multiplied by 9.8 multiplied by 7 plus half of 5 multiplied by 0 squared. The question is now, why 0 squared? Because at D, before it changes direction, it will now come to rest. It will come to a stop before it changes direction. So that is the reason why we have that 0. So if we say that we have now this answer, which is 343 joules. So we need a mechanical energy of at least 343 to lift it up. But remember, because the mechanical energy is conserved, it says still at this point moving from C until it reaches a specific point there, it will only have a maximum of what? A maximum of 250 joules. So the maximum EM is equals to 250 joules. So it basically says now the steel ball cannot reach point D. So the steel ball will not reach point B. What is the reason for that? It is this reason that available EM is smaller than EM needed. We need now to have 343 joules, but the only amount we have is just now 250. So it basically says it will not be able to reach point D. And this is basically it with this question. So it is exactly 1856. We stayed now beyond the time we wanted to work with. So if there are any questions.